So my name is Louis. I am the author of Boost.Hana, which is a modern metaprogramming library. I am also involved in the C++ standards committee and obviously in the Boost community. And I do metaprogramming. So this talk is going to be kind of an introduction to metaprogramming, but not really an introduction to metaprogramming, to classic metaprogramming. It's going to be an introduction to modern metaprogramming, really, which the title kind of implies. And the way I'm going to do that is through examples. So essentially the talk is first I start with a bit of history to give some historical perspective on what metaprogramming is, how it came to be, and so on. But apart from that, basically I present examples one after the other and explain how they work. So if you have questions, just ask them as we go. It is really important. I want that to be casual as much as possible. Okay. So it all started with templates, right? We wanted a way to create generic containers, essentially. We wanted a way to have a vector of ints, and then maybe floats, and then maybe strings, and not have to rewrite your own C style or your own thing every time. So we created templates. And obviously, we suspected that there was a little bit more to templates than just being generic containers, because a template, you can see a template as being kind of a type-level function. It takes in a function, which is the template parameter. It takes in, yeah, it's like a function. It takes a parameter, the template parameter, and then gives you back something, a type, which is for vector, you give in an int, and the return value of that function is vector of int, right? And when you get functions, if you have certain properties under your functions, you may end up with a computationally complete system. And it wasn't clear that templates were really, really powerful until someone came up with a very weird program. So in '94, some guy came up at I think it was at the San Diego C++ Standards Committee meeting, that he came up with this program. And does anybody know what this program does? Print. Yeah, it prints prime numbers. It does that in a really strange way, though. And that's what is so interesting about it. It doesn't just go and print prime numbers. If you notice, there's not much going on here. There's no printf or whatever. The way it prints prime numbers is at compile time. It does that by generating an invalid program and then using the compiler backtrace to give you essentially a list of prime numbers. Now, if I can find my way through this, I should be, D is there, right? 3, 5, 7, 11, 13, and so on. So essentially, what this shows is, so what happens here, right, is the compiler tries to evaluate the program, to compile the program. It doesn't work because the program is invalid, is ill-formed, and then as part of the diagnostic, it outputs some information, and the program is built in such a way that the compiler will output basically the prime numbers here. And what this shows is simply that using templates, we are able to compute not quite arbitrary stuff, but at least the list of prime numbers up to a fixed integer. And actually, it is possible to show that templates are Turing complete. But this does not precisely show that. But it hinted to the fact that that templates were really powerful. Really weird to use, though. Like, doesn't make much sense, right? But anyway, fun discovery. And then in 2001, Alexandrescu published this book, Modern C++ Design, which included the Locky library. Can I get a show of hands? Who has heard of Locky? Yeah, okay, right. So Locky included a type list class or type list thing. And basically, what type list is a list of types, right? So it's a little bit like a vector, like a stud vector. It's a sequence of things. But what it contains is not objects. It contains types instead. And obviously, because all of this is done at compile time, inside a compiler, you can't just go and be like, oh, I want a stud vector of, well, of what, right? So the implementation is really quirky. But it was like the first, I think, as far as I know anyway, it was the first time that someone said, hey, actually, we can have a container that contains something else than a C++ object. We can also have a container of types. And then it also provided some algorithms on type lists. So you create a type list here, and then you have like erase all. So you have a container that contains these types, and then if you want to erase all the chars from that list, you just use erase all, and then you fetch the result here, which is a nested type def inside that erase all template. And that gives you basically your resulting type list. So the mechanism for doing this is really weird. But essentially what we're saying here, we're kind of calling a function on types. And that's a type list, and then that's the type that you want to remove from the type list. And then the way of kind of getting the result is by calling result. And so you can build a bunch of algorithms like that. They're really hard to write, but when you use them, it works. And so that was basically the emergence of the notion of compile time algorithms and data structures. So just like we have the STL, right, where we have containers and algorithms that work on these containers. This showed that we could have exactly the same thing, but at compile time, which is pretty interesting at this point. So now templates are not just quirky, interesting thing to build generic containers and print prime numbers, which nobody cares really. But this actually opens the doors for much more interesting stuff. And now if we go to 2004, Abrahams and Gerteboy published the MPL book, which is really named C++ Template Metaprogramming Concepts, Tools, and Techniques from Boost and Beyond. That's a little long, so everybody just says the MPL book. And that book was like crystallizing the ideas from Alexandrescu, really. So that book made a thorough treatment of metaprogramming. It really showed that, okay, we really can have the algorithms and the data structures split, and actually we can even use the same abstraction of iterators to do that, which turns out not to be such a great idea, but that's a completely different story. And it did that by introducing the Boost MPL library. Can I get a show of hands for people that know MPL? And for people that have actually used it? Okay, good. So essentially the MPL is a little bit like a standard library. Essentially, is a little bit like the containers and the algorithms from the standard library in a single library. But all of this, type level, which makes it quite different. But conceptually, you have data structures like a vector, a list, a map, a set, and a string, for example. And all of those are compile time data structures, but not compile time as in constexpr. Compile time as in they can contain types. And then you have algorithms that work on these data structures via iterators, which are also compile time, which are essentially type level iterators. And so equal does just like std equal, right? Compares whether two MPL sequences contain the same types. So can I get a show of hands? Who knows about type threads, the header? That's great. Okay. So essentially, std is saying, it should ring a bell, right? So and for those that don't know what type threads is, type threads basically are, well, that's a whole talk, but essentially what type threads is, it gives you templates that allow you to manipulate types for doing stuff like you have a type t, you want to add a pointer to it, so you say std add pointer t, and then you have a type def in there that gives you t star, right? You have other stuff like that. So this equal here just applies, kind of is same on all the elements of the two sequences, and then tells you, oh, all the things were the same or not. And then you have other algorithms like that. And so for example, if I create a vector of types here using MPL, I use MPL vector, and then I say remove if, which is just the same as std remove if conceptually, and I give it my types, and then I give it a predicate, just like I do for std remove if. Okay, I'll talk about that predicate in a minute. So you give it a list of types and a predicate, and it gives you back another sequence. Simple enough. Now, that predicate thing is, normally you would probably use a lambda or a function object or function, whatever, when you call std remove if. But obviously, we can't just do that at compile time. So they had to come up basically with their own way of expressing, of writing lambdas at the type level. So these expressions here, they are essentially the type level equivalent of a normal C++11 lambda. And the 1 here means the first argument given to the lambda. So what this does is, for each type in this list, this lambda is called with an element in the type list. So std is void int, and then that says yes or no. And then if it's yes, then you remove it from the set of types. Is that kind of clear to everyone? Okay. So anyway, so you can go very, very crazy with this. So it provides a lot of algorithms, and it's really nice. But it's really nice, but at the same time, I mean, you have to kind of know this and like be explained a little bit what everything does. Now, in 2008, the Boost Fusion library came out, and what's really special with the Boost Fusion library is it actually merged the kind of the compile time part of things and the runtime part of things. And we'll see a little bit later what exactly what that means. Can I get a show of hands who knows about Fusion? Okay, and who has used Fusion? Okay. And so while MPL allows manipulating types at compile time, Fusion allows manipulating objects at compile time. So in Fusion, for example, you're not going to have a vector of types. You're going to have a vector with actual integers, or maybe you're going to have an int and then a float and then maybe a string, and they're all going to be actual objects. Like you can have a string that has been read from standard input, which doesn't make sense in the MPL world at all, right? But they can have different types. So essentially, a Fusion vector is like a tuple. It's the same as a std tuple. Show of hands. Who knows about std tuple? Beautiful. But I mean, I have to ask because otherwise all of this is gibberish. So like MPL, it provides data structures. So the vector, the list, the set, and the map. And like I said, the vector is essentially a tuple. The list is essentially a tuple. And the set is, well, it's like a tuple, but where everything needs to have a unique type. And the map is a little bit special, actually. It's going to map types to to objects that may have a runtime value. And these types do not have to be the same type as the type of the object to which they map. Okay? So you could say something like struct T1 maps to a std string value foo, and T2 maps to an int with value 3, for example. Not clear how it's useful. It'll become clearer later if I do a good job. And then you have algorithms, a little bit like the MPL algorithms, and a lot like the standard algorithms do. And they work on sequences, on Fusion sequences, and so on. All right? And so for example, if you create a vector, you go Fusion make vector, you should read that as std make tuple, essentially, except you can't do algorithms on tuples yet. So you create a vector with 1, and then a float here, and then I did that on purpose. Hello, is a std string, right? I'm using the new user-defined literal. So this is a std string. There's an allocation behind that. It is very much runtime. So the reason why I did this is because I want you guys to forget about constexpr for now. This has nothing to do with constexpr, right? This cannot be constexpr because there's an allocation. I could be reading that hello from standard input. So at this point, it is done at runtime. Yet the result type of my vector here is known at compile time because I know this is always going to be an int, float, a string, a double, and a char. But the value of these things is not necessarily fixed at runtime. And then I use removeIf, again with essentially the same thing as I did for the MPL, right? So I say remove the things whose types is a floating point. And again, this is an instance of a type level lambda. Okay? So what I end up with here is a vector that contains everything except the floating point, so the 1, and then the string hello, and then the char x. Is everybody on board? Okay. Again, raise your hand if you have a question. It goes downhill from here. And then the map, which I said was a little bit special. So you have a map, and then these are the keys. So you have A, B, and C are the keys, and A is going to map, and they're just types, right? So A maps to 1, and then B maps to char x, and C maps to the string hello. And then I use add key here to access the appropriate element in the map. You can imagine that as a little bit as being a struct, but instead of saying .name to access a member of the struct, you use a type to key into that struct. And in fact, under the hood, that's very much how it works. It's very, very close to what's happening. And needless to say that this lookup is done at compile time, because you know the type at compile time, so if you have a struct, it's basically the same as saying map dot something. Like there's no like runtime lookup or anything. So it's a map, but it's not really a map. It's more like a struct, okay? And this is madly useful. And now in 2010, Matt Calabrese and Zach Lane presented in my opinion, an awesome talk called Instantiations Must Go. And the purpose, the idea, the goal was to reduce compile times when doing metaprogramming. And so they introduced a way of metaprogramming without angly brackets, right? That was a little more natural, and that was expected to give much better compile times. And the idea was a little bit, it didn't really fly, but eventually, this is where I came into the picture. I kind of rediscovered this thing and created Hana, which was now possible. It was possible to do this because C++14 was now coming, and so the idea that was a really great idea, but couldn't be executed perfectly, in C++11, was now much more viable in 14. And the basic idea is that instead of representing compile time entities as types, you represent them as objects. And by an entity, I mean anything that is known at compile time, anything that you as a programmer, if you think of it, what is known at compile time is what you can see as a programmer, right? So if you see a type that you know is not going to change at runtime, because we can't change types of things at runtime, this is a compile time entity, a type. A literal, like a constant, 1, that doesn't change. That's a compile time entity too. So instead of representing them as types, like we did in MPL and in Fusion world, we now represent them as actual objects. And so Hana is basically a library that implements this idea of representing stuff as objects instead of as types. And it provides data structures like Boost Fusion and algorithms like Boost Fusion, and then it provides one quirky trick, which is to represent the types as values so that you can suddenly do everything that you did with Fusion before. You can now, everything that you could do with MPL, you can now do with this, with Hana. And so that's all you need from both MPL and Fusion in a single library. And I'm just about to show examples how you actually use that. And so again, it provides data structures, a tuple, a map, and a set. And all of these are like, compile time indexed, just like std tuple, compile time indexed, just like fusion map, and so on for the set. And it provides algorithms. It provides algorithms just like fusion. Actually, they're a little bit different from fusion in their implementation and also in their interface, but they do the same thing conceptually. And it also provides some more utilities like type here, compile time strings, compile time integers, and compile time object representation for types, which I'm going to explain just now. And the way you can do something like, before you did this with the MPL, and now you do that with HANA. And notice that basically, instead of using types here, and that's the whole point of this, instead of using types here, I'm now using objects, right? Auto something. I declare an actual variable of whatever type this is. And the variable, I initialize it with tuple t, blah, blah, blah. So that's my representation of a type list. And then the beauty of it is because I have a variable here in an object, I can use normal functions that look way more like the real STL to implement algorithms, as opposed to, say, MPL, which required colon type and angular brackets basically everywhere. Now you can use just normal functions because you're working on objects. And so here, you could actually pass in a lambda that does what you want, a real C++ 14 lambda, generic lambda, instead of something like this. And you can do also the same as you did with Fusion, so you can make a tuple with actual objects in it, and then you use, say, the removeif algorithm on your tuple to, in this case, remove things that are floating points. So t here, this is a generic lambda, t here gets basically, this lambda gets instantiated, gets called on each element, and so auto constref here is deduced to a const reference to each of these objects in order. Okay? So from within a single instantiation of the body of that lambda, I know that t has a very specific type, and this is known at compile time. Therefore, I can tell, is the type of t a floating point? And if so, remove it from the set of things. So all of this is done at compile time, yet you are using the runtime syntax. Is everybody following me on that one? Do not hesitate to ask questions.
So hang on, I'm going to step on there. So I noticed in the HANA version of that, you're using your own traits. So presumably there's something different going on there to the Fusion version, which is using studies floating point.
That's a good comment. So the question is, or rather the comment is, here I'm using my own version of the isFloatingPoint trait. So presumably there's something different going on than just std isFloatingPoint. Well, not really. Essentially, this isFloatingPoint is built on top of std isFloatingPoint, and all it does is just provide the parens syntax for doing this. So it takes in type ID here, returns a object representation for a type, which I'm going to introduce later on. And essentially what you do here, you just take the type out of this thing, apply std isFloatingPoint, and then return the value. And you basically wrap it to give the proper syntax, but that's it. So there's nothing that is meaningfully different. It is just syntactically different. Okay. And you can also have a map. So in Fusion, you have a map, and the keys are types. In HANA, you can have any type of key, as long as it can be compared at compile time. And so, for example, you can have types here, and the way you do that is you create your map, and then you say, associate type A to 1, type B to X, and so on and so forth. And since we're working with objects now, we can have some goodies, like operator bracket for a map, for example. Right? So there's no reason why I couldn't overload the operator bracket for my map, so that when you index into it, you can just use that syntax, like for studmap, for example. So that all works. OK, now the fun part. Right? And so from then on, examples only. So what can we do? One example, parser combinators. So anybody knows about the Spirit library, the Boost Spirit library? OK. Who has used it? That's good. So the idea here is we want to build a, we want to specify basically, we want to build a parser, OK? And this parser, we want it to parse any open parens, and then an integer, and then a comma, and then a string, and then a comma, and then a double, and then a closing parens. OK, that's what we, like, conceptually, that's what we want to have. How are we going to specify that? We'd rather not write just a function that says parse this followed by that, followed by that, followed by that. Like, if we could have a framework that's a little bit more general, it would be nice. And so that's what we're trying to implement, just trying to basically situate the use case here. And this is a little bit what Spirit does. Spirit basically does this and puts a nicer to use syntax on top of that, so that it looks more like EBNF. But essentially, that's what we're doing here. And so so you create your parser by using this weird little thing here that is still quite understandable, but you could put some sugar on top. And then given a string, you want to parse that, and you want it to figure out that, oh, I don't care about the open parens. I don't want to know about the value of the open parens. I just want to make sure that there is one, right? But then when you're going to parse the int, I want you to give me back the actual value of the int that you parsed. And you're going to give me that in a tuple. So when you call the parser on the text, it should give you back basically the int, the std string, and the double that it parsed. And in a real-world implementation, obviously, if it fails, then you have some, so maybe an optional, or maybe you decide to make it throwing, or we're going to forget about this. But essentially, you describe your parser, and then you would like it to return the results of its parsing. And you don't want to have to write 10,000 different parsers. You just want to have one facility to combine all kinds of primitive parsers. That's actually very powerful. And so what we're going to do is we're going to implement a primitive version of this and show how a metaprogramming library, in this case HANA, can help. But before we do that, we need to introduce compile time type information, which is this type of thing that I glanced over earlier. So the idea is, given an object, you can say HANA type ID, and it behaves a little bit like type ID, hence the name, except it is a compile time thing. So it returns an object whose type it is describing is contained in the type of that object. Okay, I know there's a lot of type words here, but so really here, so basically int, capital I, has the type HANA type of int, okay? And that thing represents basically, just says, I represent an int. That's all it says. It doesn't have any runtime component to it. And then you can use traits. You can use operations on these compile time types to modify them, right? So just like you would use std add pointer angle bracket int, now given a lifted type ID that you represent as a value, you can call HANA trait add pointer. And that gives you back a type of int star. So it's a little bit as if you were able to call traits on runtime type IDs, a little bit like that. And then this type here overloads, operator equal and stuff like that for just goodies. This here is effectively equivalent to is same, to std is same. It just says, is this thing that I have inside myself, is this thing here equal to the other thing? And the way it works is actually pretty stupid. So type is just an empty thing. We don't need anything in there, right? So it's just an empty thing. And then when we say add pointer, we can just say, well, this is not actually how it's implemented because, like I said, it's based on std add pointer. But a minimal way of implementing it is just saying add pointer. When you take a type of t, you return a type of t star. right? And then operator equal, you say, oh, when I have t and u, I say, no, 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 you're not equal. It's t and u. However, if it's t and t, now you're equal. And so you return the true type. Is everybody following me? And this is just to give a glance of like how it works a little bit under the hood, but it's not, strictly speaking, it's not super necessary to understanding what comes next. I think it's just nice to have an idea of like, oh, okay, that's basically how it works. There is not much more magic than that. There is no compiler intrinsic. There is no weird thing going on. There are no preprocessor hacks. It's just playing around with the type system in a clever manner. Okay. And now we can start building our parsers. So a basic parser takes in an input string, and then it takes a, so you're asking parse me a t, right? You're saying parse me an int, for example. So it holds the int that it's going to parse. It creates an int that it's going to parse, then it parses it using input stream. You could be much more clever than that. It's just an example, right? But so you do that, and then you just return the result. And you're so that's easy enough. And then you can provide a nice function here just to ease the creation of these parsers. Okay, so nothing too crazy so far. And notice that here in our example, we really just call the parser. So if I say, give me a parser of int, and I can just call that on some text and on some input stream, and it's going to do its parsing, right? And now we build a literal parser. This thing is a little bit more special, though. So what it does is it just ignores one character, one literal, okay? But the thing is, you don't want to return the value of the character that you parsed because you don't care. You just wanted to make sure that it was there. So you don't have anything to return, right? In other words, what I'm saying is you don't want this tuple to include the result of these parsers, which are there, but you don't want them to return anything that contributes to your result set. So the way we're going to do that is we're going to return a special type, in this case void underscore. Could be anything. It's just a special type. And we return that. And this is, and next slide, we're going to see how we use that special type to say, oh, actually, don't include that in the result set. And now that's the fun part, this combined parsers, which is the thing that you call that you call with all your parsers. So this takes a bunch of parsers. Show of hands, who knows about variadic templates? Yes. So this takes a bunch of parsers and then returns a lambda. Just because of the syntax that I create the parser using combined parsers, and then I expect this to return something that I can call on an input stream. So that's why I'm returning a lambda, okay? And I capture all my parsers using this capture here. And then what I do is I just put my parsers in an actual container that I can manipulate with HANA algorithms, because I can't do that easily with parameter packs. So I put that in a tuple, and then I say remove all. So yeah. So I call each parser on the input stream, right? And I call all the parsers on the input stream, and then I say this gives me back all the results, and then I say from these results remove all of them that are void underscore. So remove all of them that I don't care about. This is where I implement the dropping of the result of the literal parsers, basically, from the result set. I'm seeing some people agree, some people not doing anything. Raise your hand if you don't understand. Just to be sure, I'm going to re-explain this. So here, I have a bunch of parsers. I call each parser on the input stream. This is variadic parameter pack expansion. So this is like parser 1. Imagine this is parser 1, 2, 3, up to n. So I do parser 1 on the input stream, comma. Parser 2 on the input stream, comma, and so on. So I call all my parsers. Each of these parsers return its result, the thing that it parsed. And by the way, each of these by parsing, they update the state of the input stream. So they're advancing the stream, right? So each of these parsers return its result. But the literal parsers, which I want to get rid of, return void underscore. So I'm still getting that in this tuple here. And I'm going to remove them afterwards. So I remove them by saying, if the type that you're holding is a void underscore, then just drop it on the floor. And that's it. I mean, it's no more difficult than that. If you imagine trying to write that from scratch using like parameter packs or something else, it's quite annoying to write, to put it that way. OK, on to another example. A dimensional analysis. Who knows what that is? OK, quick primer. Essentially, the idea is we've got quantities, but these quantities have dimensions, right? They have units, rather. And we would like, in order for our space orbiter not to crash, for example, we would like to make sure that we don't miscompute an acceleration value or something like that, or that we don't take something that is in meters as being in feet, something like that. So here in this example, I'm having a problem because I'm trying to compute a force from a mass and a speed, right? It should be mass and acceleration. So if I just use doubles for all of these things, the compiler is not going to tell me, and I'm going to get a bad runtime result. So instead, the solution is to attach quantities to these values. The solution is to say, basically, oh, I know this is a mass. I know this is a length. And then to imbue some sort of semantics, basically, to these quantities and how you can combine them together. And then make sure that you never try to assign something that is of the wrong type to, to something, essentially. So how are we going to do that? So for this, we need to look into compile time integers. So can I get a show of hands? Who knows about stood integral constant? OK. So stood integral constant is a template that allows you to put a value, like an integral value, okay, and to represent it as basically as a type like that. So this is not really clear. So essentially, integral constant here is just a template that you say, I'm an integral constant of type int, and I contain a value tree. And then this provides you with a bunch of like, colon value member, for example, that contains the tree, and also gives you value type, which represents the T here. And it's useful for doing stuff like tag dispatching and other tricks like what we're just about to see. So this is actually part of the standard as of C++11. And I'm just going to basically take a slightly different way of implementing those. And so here what we see is, if I just say 1 plus 2, obviously I get an int. Everybody agrees with that, hopefully. And then I can say, oh, actually, here I need constexpr. I can't do static assert. So if I say, constexpr auto tree 1 plus 2, tree is an int. And I can static assert that tree is equal to tree. Everybody's good with this, I hope. However, if I do this with _c, which I'm going to show next slide how it's implemented. If I say this, instead it creates an integral constant, which contains the value 1 and the value 2 here. And then when I say plus, it gives me back an integral constant with the result of this computation. And then I can also static assert. The difference is that the value here is represented in the type of the integral constant, whereas here, all I have is an int, and the value of that int is tree. And that is a very important distinction, Here, 3 is known inside the type, which means that, for example, I can pattern match in when writing a template function and get back the value. Whereas with this, all I have is I take a function, takes an int, what's its value? Well, you have to read the value, but you don't know whether that was actually provided at compile time or at runtime or anything else like that, right? Whereas when you pass in a std integral constant, you do know it was provided at compile time because the value is as a template argument. So that's the idea. Now, how that works. So focus on the first, let's say focus on the lines 8 to 12. Okay, for now. So we write a literal, a user-defined literal, which given a sequence that of characters that represent your integer, 1, 2, 3, 4, 5, for example. We parse this sequence of characters into an actual number. So you just start with 0, and then you assume that you're in base 10, and then you just add all the numbers with the right power, and it's pretty easy to do that. So you just parse your sequence of characters into an actual integer, and then you return an integral constant that contains that integer. Okay? And so that's why if you say 1 underscore c, it calls this function, the underscore c user-defined literal, calls this function with a single character, which is 1 as a character, and then I parse that into an int 1, and then give you back basically an integral constant int 1. Integral constant looks like this. There's more stuff to it, but it's not really fundamental to this presentation. And then what I do is to be able to combine these integral constants, I write an overload of the a function template of the operator plus, and I pattern match on the integral constant, and then I just add the inner value of the integral constant and return an integral constant with the result. And it is really important to notice that I do not return an int, or in this case a t. I do not return a t. I return an integral constant which contains a t, which is the result. And this is really fundamental. Everything would break down if I returned a t. Because, for example, if I said integral constant 1 plus integral constant 2, and then plus integral constant 3, if I returned a t in the first plus, now I can't do this anymore. That doesn't work, because now I'm trying to add an integral constant with an int. And there's no way I know in that function that this int was a compile time int, for whatever that means, as opposed to a runtime int. So I can't return an integral constant from that operation. So that's, again, just like for types, this is just the gist of how compile time integers work. And now, for representing quantities, what we're going to have is basically a class that says, I'm a quantity, I have a bunch of dimensions, and then you can create a quantity from a double, you can convert a quantity to a double. I make it explicit just so that we don't get any nasty implicit conversions. And then I'm going to add one more thing inside that class a little bit later. But that's the gist of it. And the idea is when we're going to try to assign to a quantity, we're going to make really sure that we don't assign from a incompatible quantity. So we're going to if we have a quantity like mass, we're going to make sure that we never assign from a quantity of anything that is not a mass. You could build your own house rules that are more powerful, I guess, but that's the gist of it. Okay. And now we represent dimensions. So the way we do that is we're going to say, so we have only so many fundamental dimensions, so we're just going to say, oh, it's a sequence of it's a sequence basically of the power of that dimension. So mass, for example, is everything exponentiated to the 0, but the mass dimension, exponentiated to 1, and so on. Okay? And tuple C here is just a tuple of integral constants. So what I end up with here is just mass is just a tuple of these compile time integers. okay? So you can see, essentially, imagine that as being a tuple of just a compile time vector of ints. And then I can create composite dimensions. I'm kind of overflowing a little bit here, but so velocity, for example, is time over, what is I? Distance, yeah, that's right. It's easy to look stupid on the stage. I mean, I know what velocity is, right? Distance over time, yeah. So it's, one, distance exponentiated to the 1, and then times time to the -1, which is over time, essentially, right? And then you can create other composite dimensions like acceleration, where you just say, oh, it's time over time to the 2, time squared, and so on. And now the interesting part is here, where we actually catch the errors. This is the part that pays off a lot. It's really tiny, it's really stupid, but this pays off. Because now, if we try to initialize a quantity from a quantity that does not match, we can track it at compile time, because we know the dimensions of the other quantity in the type of that other quantity. We know our dimension in our template parameter, and so we can check that these two match. And we can do that at compile time, because everything's in the type of the object that is being assigned to and that is being assigned from. So we can static assert that the dimensions match. And again, what this is doing is, this is a tuple of integral constants. This is a tuple of integral constants. You can default construct these tuples. That just default constructs all the members, which are integral constants. All of these things are empty. Like, there is no runtime, anything. Just this is the most stupid default constructor you've seen. But it gives me an object of the right type, which is a tuple of integral constant with the right values, okay? And then when I compare these things, I just compare that all the integral constants are equal. So I'm making sure, essentially, that you have the same dimensions in both the quantity that is being assigned to and assigned from. And otherwise, I give a nice static assert. So that's 0 overhead, not that much compile time overhead, really. And especially given that you're going to have a limited number of dimensions, probably, and it gives you a nice compile time type safety. And now, probably what you're interested in is, composing dimensions in a free-form manner. And this is really easy to implement. You just overload the operators that you want. So here, we're given two quantities. We want to multiply them. How do we do that? So what we're going to do is, so first of all, we're going to have to agree that when you multiply two quantities, like if I get mass times, mass times length or whatever, I want to have a vector. The vector that represents the dimensions of these two quantities should add the exponents, right? So you have two vectors. I'm going to take advantage of this thing here. Can everybody see, even at the back? That's large enough? Okay, good. So I'm going to be really bold because I don't remember exactly the order in which I put the dimensions and everything, but let's say this is mass. The quantity here is just mass. And let's say mass in my matrix was the first thing. So I have a 1 here and then zeros all over. And then let's say I have acceleration. Let's say I have time. So I have time, so this one is 0, and let's say time is the second one, whatever. And like this. The product of these two should be a vector that contains 1 here, 1, and 1, and 0 all over, right? So what I'm doing, basically, I'm adding these things. And if I add a 2 here, for example, because this was a composite dimension, And I'm really bad at drawing, I bet you can tell. But I can't even write numbers, for God's sake. So let's say I had a 2 here and a 3 here for some reason. I would like to have a 5 here, because the resulting dimension is going to be, let's say mass squared times mass cubed is going to be mass to the 5. So I'm just adding basically the things. And so the way I'm doing this is a binary stud transform. So stud transform takes 1 or 2 sequences. In our case, we're using the 2-sequence case. And then it takes a function that takes 2 elements and then just applies the function on pairs of elements. And then that function gives you a return. It returns something, and it puts it in the resulting sequence, right? That's how stud transform works. So this binary transform that I'm using, which is called zip width in HANA, would probably have been better in retrospect to call it just transform. But this is taken from the functional programming world. And so basically what I do is I take a function f in this zip width, and I call it with elements, these elements, and then f on these elements, and then on these elements, and on these elements, and on these elements, and every time I get back a result. And I put that in the resulting sequence. And the function the f that I'm using is plus, stud plus, which just does basically operator plus on the 2 things. So what I'm doing is, in lockstep, taking the integers, integral constants from each sequence and adding them and producing the sum of these 2 things, the in lockstep sum. And then I just pull the actual value out of each of my quantity, and then I just create a new quantity that represents that dimension, the new composite dimension. Is everybody following me?
Yes.
Okay, good. And for the operator divides, basically the same thing, but you use operator minus. Yes.
Just to be clear, could you please remind me what the type is of these dimensions? Would be 1 and be 2? Is it an vector? Or
Okay, so the question is, what is the type of these dimensions, D1 and D2? Is that correct?
yes.
It is a HANA tuple containing HANA integral constants. So conceptually, it is a vector of compile time integers, or a compile time vector of compile time integers. Yes. And this is why, and since everything's so compile time and so empty, I can just default construct the hell out of them. Like they don't have a runtime value, and like they're const expr default constructible, trivially copy whatever. They're just compile time stuff. Yeah, I don't really the only thing I care about is their type. But because I don't want to be stuck in the MPL world where everything's a type, where you need type name everywhere, and where you need to have angly brackets and crazy stuff, I default construct them. But really, I'm not doing anything different from MPL here. I'm just using a different syntax. Yeah, so these are just tuples of integral constants. Yes? The question is, why is this static cast to double needed? So if I do not static cast to double, I'm going to get in a really bad case of infinite recursion here, because A is a quantity, B is a quantity, and so operator star is going to be called again, and now you just get yourself in trouble. But regardless, I mean, it's just because I declared that could have been a.get, and then I could have defined get as being give me the actual double value that you wrap, right? It's just that I decided to use an explicit conversion to double, but yeah. So here I'm just saying, hey, I took care of the type computation associated to your runtime computation. Give me your runtime value, please. I made sure that it was okay. Yes.
Why do you provide a template constructor that takes the wrong dimensions and then static inserts it? Why not provide the normal constructor that doesn't take other dimensions? If you go back a slide. That one there. Why provide that constructor at all? Why not provide one that
question is, why do I provide this constructor, which is a template, as opposed to just a constructor that takes the right dimension? This is a valid implementation choice. I liked the fact that there was going to be a static assert telling me exactly what's happening, as opposed to no matching constructor, blah, blah, blah. That's one thing. The other thing is, actually, if you decide to, if you, no, so what he's suggesting is, no, what he's saying is you could just have said, well, tell me if that's what you're saying. You could have said, basically, provide a non-template constructor which takes a quantity of dimensions. And then if you try to pass anything that's not dimensions, like if you try to pass if you try to pass time and you had mass, there's just going to be no matching constructor. It's going to be the wrong type. Is that what you're saying?
Yeah, it's not a copy constructor.
Exactly, yeah. So yeah, like I said, it would kind of achieve the same thing, but you wouldn't get as nice as an error message. The other thing is, this is actually going to work if for example, you have integral constants from stud and from Hana in the vector, because this does like a deep comparison with equal. It checks that the values are equal, where the other one is going to be an exact type match. So if you have like one dimension specified with a tuple of stud integral constant, and the other one is a tuple of Hana integral constants, it's not going to work because they're different types, but they could represent the same values.
But doesn't that break stud is convertible, you're going to say? It appears to be constructible, and that's to them, but only a static assert, which is far too late, but is convertible to actually help you type create that.
Okay,
Whereas
so
if you did it in a spinnated way,
yeah.
it is the ugly, but there is the value to
Yeah.
Not break is convertible.
You're right. So first of all, okay, so the comment is, doesn't that break is convertible? Yes, well, this one doesn't actually, because this is explicit, so you need is constructible. But that's a nitpick, right? Yes, in essence, you're right. Yes, this is breaking is constructible. It's just an example, but essentially what you could also, if you didn't want to break it, you would say stud enable if dimensions equals other dimension. And then at this point, the advantage that you have over having the exact type match is what I said about stud integral constant and Hana integral constant. You get more interoperation, but you do not get the static assert message. And actually, for real world use cases, I would probably say it's a bad idea to have such an open constructor. These can become hell in very subtle cases. But the essence of the technique that I want to show is not so much about enable if and the details of how you should enable or disable your constructor. But it is a very valid observation. Thank you. Okay? So you can compose dimensions. And that's it for this example. Any other question before we move on to a different example? Question is, how did I define Hana plus for the integral constant? Like this, essentially. Takes two integral constants, returns an integral constant with the plus of the values.
The question is why you don't use STD ratio
to express the
units. It will be nice to have to express mass for kilograms or grams and use the same as acidic chrono for seconds, hours, and
okay, yeah. So the question is, why am I not using something like stud ratio, for example, for expressing fractional dimensions, the exponents, basically. I guess it's just too sophisticated for this example. This is just about basically this example is meant to showcase a little bit like how you do this and how you can use this binary transform thing. And I mean, I guess, well, might also argue that this is a little bit over-engineered because this just does the job but this, you can explore. There has been a dimensional analysis library written with HANA. I don't think they do that, but they probably go much further than this. This is just a conference kind of example. Yes? Why do I use decal type? Because I made the mistake when I designed that library, which I now consider to be a mistake. I'm sorry for my users, but to make this an object. Because the idea was everything's an object. We don't ever need types. Everything's auto. That was kind of the design. That was a tenet of the library at first. And then here, it's easier for me because I'm passing them in as template parameters here. So it's easier for me to define these things. Like you probably want to have like a global type def, right, that says this is mass. And in that case, it does make sense to have a type. So what I need to do here is basically the decal type of that tuple. But what I would have considered a better design decision here is to make that tuple C should probably have been just a type. And then if you do need an object of that type, it's really easy. Just add curly braces and default construct it. Yeah, HANA 2.0. When I break backwards compatibility, I'm probably going to make that change. It is a valid observation. OK, I'm going to move on to the next example. All right. So let's say we have a system in which we are able to, we have a set of events, and we basically can register callbacks to be triggered when an event is, to be called when an event is triggered, and we can trigger events, obviously. That's the two things we can do. It's pretty simple. So here I have an event system. The set of events that I know about is foo, bar, and baz. And then I say, on foo, you're going to execute that lambda. On foo, you're going to also execute that other lambda. So you might have more than one callback associated to an event. And on bar, you do this, and so on. And then here, you just say, oh, trigger foo, trigger baz. And if you say trigger something that doesn't make sense, probably it throws, or maybe it does nothing, or maybe it's a runtime error. Like, who knows? I mean, this is, at this point, it's unspecified. OK? So that's kind of the problem we're trying to solve. Now, imagine that your events are known at compile time. So like we're taking a very broad problem, and now I'm going to put some requirements and show that we can use metaprogramming to actually do that in a really cool fashion. So imagine that you have all your events are known at compile time, which is sometimes a very valid restriction. Sometimes not all problems call for a fully general thing where you can add new events at runtime. So imagine that you can all your events at compile time, and also imagine that you know which event you're going to trigger at compile time. So whenever you call this trigger here, it's always with like a literal or something that could be a literal. It's always with something that you as a programmer know that, oh, in this case, I need to trigger that event specifically. So under these two restrictions, can we do better than just the naive approach? I claim that we can. So the way we're going to do that is we're going to create an event system where these things are compile time strings, and I'm just about to explain what these are. So these are compile time strings representing the set of events that the event system supports. And then when you register an event, you give the name of the event as a compile time string, the lambda, the callback. And then if you try to trigger an event that is unknown, you should get a compile time error, not a runtime error. And it is legit to expect that because you know the set of your events at compile time, you know all your events at compile time, and you know what you're triggering at compile time. Like, technically, conceptually, you don't have any information that is only known until you run the program. So we should be, normally, we should be able to get some, also, to diagnose the misuse at compile time. And we're going to build that. And if you try to, if you try to register a callback for an event that doesn't exist, it doesn't work at compile time. And same if you try to trigger an event that doesn't exist. It doesn't work at compile time. Okay? For that, we need compile time strings. What are compile time strings? So just like we took types and then represented them as objects with the type ID trick. And just like we took integers and we represented them as kind of augmented objects with integral constant, we're going to do just the same trick. Nothing new. Just the same trick for string literals. So here, underscore s, just like underscore c did, underscore s is going to create an object that represents a compile time string. Plus is going to concatenate these compile time strings, just like std string does, but everything's done at compile time. And then given a compile time string like that, you can say, oh, are you equal to another compile time string? And possibly you could also implement arbitrarily complex operations. So essentially how that works, and here I would like you to focus here for now, you define a user-defined literal, which takes a bunch of characters, which represent the characters inside the string literal, and then you just create an empty object, just like our integral constant was mostly empty, our type was mostly empty, what was completely empty actually. You create an integral constant, sorry, you create a string here with the right template parameters, and you just default construct it, you don't care. So what you've done is encode the value of the string literal inside the char parameter pack. And then when you want to compare these things, well, you get two strings with two sets of characters, and you just want to know, are all the characters equal? And now there's a bunch of ways to implement that. One is to say, oh, are you the same type? If so, then you must contain the same set of characters. You could use C++ 17-fold expressions to compare. Guess you could do that probably. Anyway, like pick your implementation, it doesn't matter, but the idea is, are all these characters equal? And you could also probably be fancy and say like, if there are many null terminators, what happens and stuff like that. But the idea is essentially you're saying, do you contain the same thing for some definition of same thing? And then when you say plus, just the same as we did for integral constants, you take two strings and you just concatenate them. Is everybody with me here? Okay. So again, this is just the gist of like the idea behind that. Now we're going to build the event system that I described in two. We're going to build two of them, one of which is the first that the two have the same restrictions, the same requirements. One of them is like the naive or the classic implementation where we're going to use an unordered map to store the mapping from events to callbacks. The other one is going to take advantage of the fact that we know that all this information is known to compile time, and we're going to use HANA map instead. So for the first one, the runtime system, we use an unordered map from strings, which represent our events, to a bunch of callbacks associated to that event. Okay? And in the other case, we assume that we get a bunch of events, which are compile time strings, and given that, we create a map that map each event to a vector of callbacks, just the same as before. So notice that the only difference here is basically that I'm hard-coding the name of the events, which are compile time strings given to me here. I'm hard-coding that in the type of my compile time map, which is going to allow me to do all kinds of interesting stuff later on, okay? Now, when we create the event system, at the runtime, we need to get a string of the events, the events that are valid, so that we can insert them in the map and say, these are the events that I know of, right? And at compile time, we don't do anything, because the default constructor does the right thing. Default constructor is going to default construct this map, which is going to default construct all of these pairs. Each of these pairs is going to default construct its own compile time string, which is an empty thing, and its own std vector of callbacks. And default constructed in a vector is just going to put the vector, an empty vector, which is exactly what we want. So when we do this here, we're basically creating an event system that has a bunch of empty vectors, one for each event that we said we needed. Okay? And now, when we want to register a new callback to an event, in the runtime case, we take an event as a string and a callback as a function, and then we try to find the callback in the map of all our events to set of callbacks. If we can't find it, then we did a mistake because we tried to to add basically a new callback to an event that did not exist, which is an error in our current spec. And otherwise, we just add the new callback to the set of callbacks that was associated to that event. Everybody's with me here for the runtime part? Okay. In the compile time world, we take an event, which again is a compile time string, which is why we have a template parameter here. And we take a callback. And then we say, is that an event that I know? Since the name of the event is a compile time string, and the set of events that the event system supports is a bunch of compile time strings, right? Because they're in my HANA map, which is all compile time and nice. I can ask the HANA map, I can say, do you contain that event? And it's going to tell me for sure at compile time, yes, you contain that event, or yes, I contain that event, or no, I don't, right? So this auto here is going to be an integral constant of true or false, which I can then static assert on, because I know the value inside that integral constant at compile time. And this is the magic here, right? The magic is that I know my event name at compile time, my map knows the keys it contains at compile time, therefore I can tell whether it contains one of these keys at compile time, therefore I can do a static assert instead of an assert. And this is where you actually this is precisely where you catch your mistake, at compile time instead of in the release of to the client or whatever. And then you go and you say, give me the set of vectors associated to that event, and then push back, right? Push back that new callback inside the set of callbacks that you have. And there's another really interesting thing going on here. This upper bracket doesn't do anything. Why? Well, because remember what I said when I talked about fusion map. It's basically a struct. You have the set of things, you have the set of entries that you contain in the map. All of this is known to compile time. Essentially, the way this is implemented under the hood is like a struct, where if you say, where you associate a compile time string with a member. So this operator bracket, the bit before the pushback, is essentially, actually it is equivalent. It compiles down to the same thing as a dot name access inside a struct. So you are saving an unordered map lookup. I mean, it's a cool benefit, I guess. We're going to see later on whether it actually matters, but at least you know that you're doing the least amount of work that you can ever do. Like if you wrote all of this by hand without any template metaprogramming, you would have a gigantic struct probably, and it will be quite complicated, but you wouldn't do any runtime lookup, which is good. Well, now you have a really tiny and reusable component, and you're still not doing any runtime lookup. And now, when you want to trigger an event, it's a little bit the same thing. So you get the event as a string. You try to find, in the runtime case, you get the event as a string. You try to find the event. If you can't find it, then you say, oh, we messed up. And otherwise, you go in and trigger all of the callbacks. In the compile time world, you get an event as a compile time string. You do the same trick. You say, do you contain that event? You know that compile time, so you can assert, static assert rather. And then you do the lookup to get a reference to the vector that contains all of the callbacks. And you iterate over that vector, and you call all of the functions associated to that event. Is everybody with me? Yes.
Why is the compile time case not possible just standard?
So the question is, why is the compile time case not possible just in the standard? What, a literal map? Well, so do you mean actually using, I'm looking at you like that because the distinction is very important, so I'm going to try to understand exactly what you mean. So do you say, why can't stood unordered map, when you pass it a string literal, why can't it do that?
And say, what is it that we're missing in standard?
Well, you're missing HANA map, essentially, if you want to do that, which is in that library.
And where does the stood map fail in this example?
So you mean, what is the let's say if you compare HANA map to a stood map, like does it actually matter that we're doing this stuff at compile time and so on?
Yeah, is it not? The question is, why is it not easily doable with the stood maps?
Okay, the question is, why is it not easily doable with a stood map? Well, because the map, when you write the map, you don't know that your key is known at compile time. You must assume that you don't know that your key that you're keying on is known at compile time. So you can't do anything of this, basically. You can't possibly implement the lookup at compile time, right? How would you know when you write operator bracket for a map? And let's say even easier, like a map that takes strings and then maps to something. How would you tell that this string was actually like a string literal and that its value was foo? You can't do that. You have to store that information in a type of the string that you're passing, which is compile time strings. Probably we can, I mean, is there a vast majority of people that would like this question answered on stage? Mm-hmm.
Is the difference really just object generation at compile time with HANA versus stood map? Is that really kind of what you're saying?
So first of all, I'll just finish up with the previous question.
But I think that question is related to that. Like in HANA, you're generating the map and the key at compile time, and stood map can't do that.
Yeah, okay, so yes. With HANA, I'm generating the map at compile time, and the stood map can't do that because it's a hash table, right? It must assume that it's a completely different beast. It must assume that maybe you're going to insert stuff in it, and you're going to maybe erase stuff from it, and so on. So it has to be mutable. I don't have these requirements. Not only that, but I also know the value of the keys that I have in advance, which means that if I was to even want to build a hash table, I could at least do a perfectly hashed hash table, right? I could figure out the perfect hash at compile time. So I've got more information, and I'm taking advantage of it. After the talk, let's talk together. I think I know the answer to your question. I think I know the answer that's going to satisfy you, but it's going to take more time than I can spend now. I'm actually a little too tight. Okay, so right, we call the callbacks. Easy. Okay, does it actually matter? I mean, there is the fact that you're catching errors at compile time instead of runtime. That may or may not be really, really cool for you. But what we all like, because we're C++ developers, is usually performance. So let's have a look. So I compiled a toy program with O3 and FLTO, so link time optimization. So probably what the highest level you can expect. And then I did a bunch of I inserted the same thing in the two maps, right? A stood unordered map in a HANA map. And I basically then I triggered that number of events. So 2, 4, 6, 8, and 10. And these are times 10 million events. This is like 40 million events. And then I just triggered them and I just time to see. And the idea is all I'm interested in is not so much the actual time difference. I don't care about that. All I'm interested in is, does the compiler do a really good job at optimizing a unordered map, a stood unordered map, when it can see very easily, because it's really a toy program, when it can see easily what I'm actually putting inside that map and what I'm actually fetching inside that map? Can it easily optimize all of these lookups away? That's what I was trying to figure out. So I would be happy with just a little difference that tells me, oh, the code gen is different. And now the answer is really obvious. For a HANA map, it's actually hidden by the stood function here case. So there's essentially no overhead besides the looping over the vector and doing the calls. And here you actually pay for the unordered map lookup, and then for the calling the callbacks. Stood function here is I took the same case and I wrote it by hand, basically. So I knew the set of events I had, so I created a struct with a bunch of stud functions, and then I just call these stud functions as if I was writing it by hand. And the idea is HANA going to add anything to what I could write, let's say in C or whatever, without any abstraction technique? And the answer seems to be no. I don't think there was much of a difference in the assembly. So at least for not too convoluted use cases, it doesn't seem, we don't seem to be paying too much for that abstraction, which is interesting. Of course, as with anything, please don't take my word for it. Just benchmark, and then if HANA does a really bad job at, if HANA generates really bad code, you can file a bug report, and we'll try to see why that is. Now, what if we need to relax the constraints, and what if the event can now be decided at runtime? So you don't know, like you're maybe reading from standard input and determining like what event I should trigger based on that, which is probably closer to a real world use case. So here, I'm reading something from standard input and then triggering that event. So I can't possibly do anything at compile time inside that trigger function because I don't know the value until runtime, okay? So what I'm going to do is I'm going to maintain a dynamic map. I'm going to need a dynamic map because I'm going to do some runtime lookup. So I maintain a dynamic map, and notice here that my dynamic map is going to contain a pointer to the callbacks. What I'm going to do is my dynamic map is going to map each event to the set of callbacks in my compile time map, which is still around, okay? And then basically I'm just going to do that linking when I create my event system. So for each event, I insert an event with the right address, which lives inside my compile time map. That's my runtime map, that's my compile time map. And I just insert basically in my dynamic map the address of each vector of callbacks, right, in the right place. So I'm setting up basically links between this dynamic map and this compile time map. The only purpose of this is just to avoid having to, I'm just going to need to update one of these two maps, right? Actually, I'm just going to have to update the compile time map when I add a new callback, and it's just going to do the right thing. Now, what do I do? Well, it's actually pretty simple. I just have to overload trigger. I just say, hey, by the way, if you're not taking just any compile time string, if you're taking a stud string, something that I can't do anything intelligent with at compile time, then you fall back to the dynamic lookup. And at this point, the dynamic lookup is just the same as a runtime case. Basically, you look at runtime in your dynamic map, then you do a runtime assert. You can't do better than that. So you do a runtime assert if you can't find it, and then you go look at the set of callbacks that are pointed to in that, by that entry in the dynamic map, and then you just do the same thing as before. So what this example shows is essentially that it's really easy to bind compile time and to take the most out of your compile time information that you have using HANA, and then, well, just fall back to runtime when that's what you need. But you shouldn't leave, or you have the option not to leave this additional information on the table by using metaprogramming. And if you want to stay sane, you should probably try to use HANA instead of hand-rolling it. And what about performance with this? So the idea is, oh, is it going to be much, much, much worse? Well, it doesn't seem to be much worse. So HANA seems to be outperformed a little, slightly for kind of large number of events. What you could do also to avoid that, you could basically always update the two maps and not store a pointer, so you would avoid like one pointer chase, if that makes any difference. Also, you could just rerun these benchmarks for yourself, and maybe it would change. I don't even know whether that's noise at this point. So, more or less, it doesn't make a large difference, and again, just benchmark for your own stuff. So, but it's definitely not like, because you took advantage of the compile time stuff, you didn't leave all the runtime performance on the table either. You can kind of have both, which is pretty important. And so this is where HANA really shines. It's when you combine compile time and runtime together. This is where it becomes really easy to do that. And now I have 5 minutes left, and I still have at least one example, and I want to know, and then I have a few slides on what I think is the future for metaprogramming. And I'd like to have a quick show of hands. Who would like to see more examples instead, and so either more examples or the future? Raise your hand for if you want more examples. Raise your hand if you want the future. There we go. So it was about generating JSON. I've shown that example in previous talks. Everything's going to be online. You can just look at it. It's also in Hana's example directory. So like, there's a lot of stuff you can just copy paste and play around with. Future. So what are we going to have in 3 years or 6? 20 or 23, not clear yet. So consider trying to serialize stuff to JSON. Let's say you have these structs, and you want to write a to_JSON function that generically, without knowing about tetrahedron and point and triangle, without knowing about these things, is just able to, you feed it some types, and it just does the right thing, like Python can do, like most other languages can do. How would we write that? So should output this. So there's a bunch of ways that we are currently considering for doing this. By the way, all of this is like me rambling essentially. So like none of, we might never see this in the standard, but these are the things that we're currently talking about. And if you look at the standard papers, like, some people are proposing things that are very much along those lines. So we might end up with something that looks like this a little bit. So basically, if you take in an object, if it's a record, that's a const expr if, right? So this if is basically, it's a static if, then a compile time. So if t is a record, and then you use a reflexper keyword to get back some kind of representation of the type that you can act on. It's a little bit like our type ID, essentially. It's a little bit like our type ID, where you take a type and then you get an object on which you can do more interesting stuff. And in this case, you can ask, look, are you a record? Which is probably like a concept that says, oh, you're a user-defined struct with some nice properties, like no private members or whatever. And then you say, give me the set of members, which returns like a sequence of maybe which returns a sequence of objects that represent the member. So from that thing, you can retrieve the name of a member in the class. You can retrieve a member function, member pointer to the class, to that member in the class, and so on. And then some way of iterating at compile time on these objects, so that you can say, or just having a kind of a const expr. Basically, I here is a constant expression, which means that you can use it to index into that const expr sequence. And the interesting part is that members, each element of the members here have a different type, because maybe you have a member that's an int, maybe you have a member that's a float, and whatever. So you have a member pointer, the member data pointer to an int, and then that to a float, and so on, which are different types, right? So they need to kind of have a different representation. And then you just output each of the members, right? And that's it. So these are the kind of things that we're thinking about. So more static control flow, essentially. And that's for like doing runtime computations, and mixed with compile time computations. The compile time part has to do with reflection, and the runtime part has to do, well, here, I'm outputting stuff to an output stream, so that's obviously very runtime. And now the future of type level computation, well, imagine here that you want to sort types by alignment, which can be useful for packing, for example, or doing stuff like that. So imagine that I could that I had a type that represented basically the return of a reflexper earlier. Imagine I had a unique type that could represent a type at compile time. And imagine that I could create a std vector at compile time, because I could do, for some reason, allocations in const expr, which we can't right now. We could just create a vector of types and then sort them by alignment. And the algorithm just looks like, well, you give me a vector of types, and then I sort them using std sort, not HANA sort, not MPL sort, not Fusion. Fusion doesn't have it. Not anything, just std sort. That's pretty awesome, right? And then you just go, given a type T and a type U, sort them by alignment.
Are you that pessimistic about ranges?
Oh, am I that pessimistic about ranges? No, no, not at all. It's just an oversight, I guess. But trying to put too much stuff in the same, another talk for ranges. Plus, I don't know that they currently support. Yeah, it would be a bad idea to mix the two together for now. So you get a vector of types, and then you just sort it. And beauty here is you can use std sort because these, unlike the HANA type IDs that I showed earlier, these are homogeneous. They all have the same type. So you can use all of the current C++ that we have. This, in my opinion, is the future. We'll see whether that can be made to work, but anyway. And then once you have this constexpress to the vector, what you want to do is actually influence your program with it. The way you do that is we need some kind of way of getting an element of a, from a std meta type back to an actual type, and then some way of extracting the elements of a compile time sequence into something like a parameter pack or whatever so that you can influence type. So here this is creating a std tuple with each element extracted from the sorted sequence, and each element is a std meta type, but it's known as compile time. So if we create like a new magic keyword or reuse one, we might be able to actually put that out and represent that as a type. And so I see, I think, 4 steps to get there. And I'm a little bit over. I'm almost done, though. Feel free to leave if you want to leave, though. So first step is to expand constexpr evaluation to allow some allocations, which gives us basically variable size sequences like vector in constexpr. We think that's possible, but we're not sure yet. But it should be possible. There's some very deep implications to that. And then create something that we can use to, basically a compile time RTTI. So something along the lines of a meta type or whatever. Some way of representing a type at compile time. And under the hood, by the way, it's usually implemented as a pointer to an AST node inside the compiler, which is pretty neat if you think about it. You're really playing around with the actual AST representation inside the compiler. And then given a meta type, you want to extract that back to a C++ type so that you can actually influence the AST back, right? And finally, although it's not strictly necessary, I think it's highly desirable to take anything that is more or less a compile time sequence and then expand that into something with which you can influence your program, most likely a parameter pack. So that gives us the ... here, which is required if we want to populate, for example, create a tuple with the most packed alignment. Anyway, so metaprogramming is powerful. I hope you're convinced. If you're not, come talk to me afterwards. I have a few other examples. It can be cumbersome, but you end up with something pretty powerful. I think we need more metaprogramming, frankly. I think we need more metaprogramming. If you look at other languages, especially dynamic languages, they do crazy things, really interesting things. Sometimes a little bit too interesting. But I think we do need less template metaprogramming, though. So I think a lot of the bad press that metaprogramming has had is because we don't have the right tools for that. And HANA's a pretty good step in that direction. I do think that we need language support. We're working on that. But anyway, so I do think we need more metaprogramming. I wish that we can embrace this reality, and all of us are moving forward towards that. And that's it. Thank you very much.